lunch together, and he brought his children back to the hotel room. So he will come back to us to our classroom later when we have discussion. So now I will continue on my presentation, and later on my TA will come up to introduce about our project. So let me finish my slides first. So there's a second student who works on soft mechatronics. So there are three parts that were done by this second student. So first of all, he used 3D print. It's a kind of material that can be printed, and also it has a little softness. So this process is very similar to is my student directly print out the device. You guys print out the mold. Okay. After that, he apply a kind of piezoelectric material at the fingertip. The purpose of this material is to serve as a sensor. So in the future, when this gripper grasp, share, 这样音乐关掉。Okay, I can have music. It's fine. Okay, thank you. Okay, so he apply a kind of sensing material at the fingertip. It's a piezoelectric material. So when the gripper grasp an object, the sensing signal will recognize, okay, the robot grab something. So over here is the part where he analyzed the signal. He used an amplifier and convert the analog signal to digital, use a computer to analyze it. So once he has a sensing signal, he use a monitor to study the behavior of the gripper. And there's a controller for the robot. So he put this whole thing underneath the robot arm, an industrial robot arm. And also use a circuit control to control the pressure, because this device is also actuated by pressure. Okay, so from here you can see it's a very complex system for this research. So this is what he has done. He printed out this design. You can see there are some air channels. So later on, he will pump gas from the back, and he use a O-ring to seal the gap, and use screw to tighten this structure. So when high pressure comes in, these air channels will be expanded, so the finger will bend. Okay, and this finger is made of TPU. Now, the final finger looks like this. In his research, he tried to design this geometry in different dimensions. So also later on in your design, maybe some of the dimension needs to be changed to have better performance. He used a camera environment with lightings and a camera to take a picture of the bending finger. So he also used image processing to study the position of some red circles. And later on, he a second design. At the beginning, he didn't do anything at the bottom, but he wants to have more flexibility at the finger, like a fingertip. So he made some kind of like a spring structure at the bottom. He want this gripper has a softer touch. So that's what he did. Basically, he made some structure like this at the bottom, right? Like this. By the 3D printer, it looks like this. Okay. And this is where he applied the piezoelectric material. It's a mixture of graphene and something called PVDF. PVDF by itself is a piezoelectric material. But if you want to have piezoelectricity, you need to apply electricity field. So this the atom direction electric material. However, carbon structures. When you mix them together, those flat graphene structures will allow the PVDF. So of mixture. Taiwanese, what is this? 压电材料. When you compress, there's electricity coming out. So later on, we are in this course, we are not going to use electricity. However, if you are interested in graphene mixed with PVDF, you also can use this. I have already talked to Professor Hong from Applied Science. He's okay with this. So if you want to try this, it's okay. We will see more of this information in the following slide. Okay, so I hope this is a video. This is a soft gripper grasping a ball and studying its signal. We try to grasp a ball or a cup. Okay, here's a video. You can see when the we actuate the finger by pressure, and when the fingertip has contact with the from the sensor. Okay, so this was done in the past, and we use some kind of filter to process the data. Okay, to analyze the data, and we use Fourier transform. So basically, for every data, originally it's in the time domain. So the signal when you receive the data, it's in voltage. So it's a voltage data vs time. If you apply so-called the Fourier transform, then you can convert the data into frequency domain. You can see there will be a peak because we apply this grasping in a constant frequency. So that's why you will see a constant peak for the data. So that was if you zoom in, you will see there's a 2 hertz peak right here because the grasping frequency was 2 hertz. Okay, and we also this is like modeling. We try different pressures for applying the gripper, and we study the response from the sensor. And we try to see if the sensing signal shows different amplitude when you apply different levels of pressure. At the end, we found when you apply greater pressure, you have greater deformation. So when you have contact with the object, it has a greater grasping force, larger force. So we found a relationship. The larger force give us larger voltage. So greater voltage when you apply greater pressure. That's why you have some model like this. How come they are linear? Because we chose a linear model. We didn't apply too many experiments. If you apply a lot of experiments, maybe this relationship is not linear. But we didn't do enough. That's why we can only use a linear model. You can see the standard deviation is quite large. Okay. This is about vision-based soft gripping. So every application, we try to use a camera to observe working environment, trying to later on move the robot arm and then grasp. What my student did So this was done by the same student. He used a controller like this. This is a power to provide power to many computer code right here, and then through this Modbus protocol, inform this controller, and the controller will control the gauge, the valve right here. So it will turn on the valve how much you want the pressure to be. And I think, yeah, this is a video. So at the beginning, you can see there are some, when there is a vibration, this material has some signal. But after grasping, that signal will be more significant. Okay. So on top, there's a video, there's a camera recognizing the ball, the position of the ball is being sent to the controller, to the computer. Computer decide how much, and the piezoelectric sensor will identify, okay, there's grasping, and then proper grasping. So continue for grasping a ball based on image signal, and also identifying whether you signal. I think this is grasping the cup. I remember the student was meant to apply different forces because cup is weaker. If you apply the same pressure, then you will break. You may break the cup. So I'm not sure if he used any kind of feedback control. So supposedly he should study the signal and realize how much grasping force is applied to the cup. When it's enough, then you don't increase the pressure anymore. So later on in your project, if you can, try to use the signal from the sensor and use the signal to decide how much pressure you apply to the device. Okay, here's a third student. So I don't know why many of my students enjoy this topic. So a third student work on this robot. So the previous student designed this gripper with very small deformation. This third student changed the design, and he realized it can perform a much greater deformation. And also, she embedded the piezoelectric sensor inside PDMS just to protect the membrane. So because there's graphene inside, graphene in Taiwanese is 石墨烯, so it's like a carbon inside. So the color is black. So the mixture of graphene and PVDF allows this membrane to have piezoelectric. So she also applied at the fingertip. So basically, she did similar research, but the finger design was different. And she this time, I think she tried different printing material. And the first one was done by the previous student, and the last one was done by her. And she claimed her new design can bend with larger angle. And everything else is quite similar research. But this time she used a standard measurement uh, setup to identify how much force that is applied to the sensor and identify how much signal will occur when the force is applied to the sensor. So he built this setup to figure out the modeling. And okay, maybe here it will be more interesting. This is how the process of the making. From the Professor Hong in Applied Science, they can provide a mixture of PVDF and graphene, and they will teach you how to create a thin layer of this mixture. When it's cured, you can cut into small pieces, and then you can use a copper tape to connect the wires. So whenever this thin sheet of membrane deforms, it will generate some current. Okay, and for the protector, we use PDMS, and then we just put the sensor inside. That was how the sensor looked like. I think I will skip this. I don't want to spend too much time. Basically, she did a lot of modeling, and she put the sensor right here at the middle, and there's a weight right here applying, like clamping the sensor. And do this, but you can try to learn from it. Okay, there are standard measurement experiments for you to build a model. So from here you can see she did this is D33 means so it's a unit represent piezoelectricity, how much the certain amount of force, and this is the force being applied. Yeah, that's what she did, a lot of modeling. This is like linear models, force versus voltage, nonlinear models, nonlinear models, different kinds of nonlinear models. Okay, so similar setup. pressure applied to at the fingertip. You have piezoelectric sensor. Use data loss. Use systems to combine together to perform what you are trying to do, uh, which is properly control the pressure. Okay. I hope this is a video. No. Let me see. No, it's not a video. Yeah, that's what she did. She also did grasping and releasing, and she tried. For sensors, it's a time dependent signal. It has up and down. Do how much do you use from this time dependent signal? For her, she just pick up the tips, the peaks of the signal. Use the peak information has more uh, representative value to represent the level. Maybe you can use a different way to study the signal you receive. Okay, so I will skip many of those. Now, there's another student who follows the third student. So this fourth student working on the same topic. But this time, person has a soft body and hard skeleton. He tries to have grasping motions more like a human hands. Okay, so over here, he used some motors to define different ways of grasping. So we want to define a gripper that can reconfigure the finger geometry. I will show you how. So for the soft part, this is basically the material you are going to use this time, so-called the seal skin. It's a kind of silicon rubber. They are usually two bottles, and you can mix them in a 1-to-1 ratio. If you mix them in a different ratio, it either becomes harder or softer. So you can try different combination. And he built it in a very common way where you have multiple air channels at the center and blow the air from one end. And this is how everything was done. I think because of this student, many of the future students follow his the procedure he made. Okay, so even for the training in the following 2 weeks, geometry were made mix the silk skin assembly of the parts. Okay, so I think my TA will introduce more about the procedure later on. It's quite soft. So for my students, he wants this soft finger to be stronger. That's why he apply the skeleton. And I think this is he believes this is for his thesis. When you work on your thesis in the future, I think everyone wants to get a master degree in the future. When you make something, you want to make up a story. You want to say you learn from the nature. But trust me, he didn't come up with an idea at the beginning. Just one day we decide, okay, how about learn from the nature? So he decided, okay, he learned from the shrimp. The skeleton came from the shell of the shrimp. So what he did was outside of the soft geometry, he built the different layers of the shell. Some portion of the shell to change rigidity of different parts of the finger. So when the shell is not tightened, the entire finger can freely bend. When you tighten some part, that part become more rigid. So that part will not bend too much. By changing the rigidity at different portion of the finger, he can change different bending shapes. Okay, so over here you can see on the right hand side, um, the third figure right here, he tightened the shell for this portion of the finger. So when you apply pressure to the finger, only the apply pressure to the entire finger without tightening the shell. This finger can actually bend a lot. So by doing so, he generate different ways of bending. Let me show you how he did it. It's a very complicated design, but he successfully make it done. He generate many small structures for the cable, not the cable, for wires. So he apply cables. He apply three cables or wires. When you tighten the wires, that portion of the shell will be tighten up. So you can see first first wire was passing through multiple positions. This is a second wire and a third wire. So that's what he did. You can choose to tighten different wires. Okay. So here's a demonstration. The left figure shows these three parts is loosened without tightening. But if you pull the blue wire, this part is tightened. So now he has many different ways to tighten the finger. So so now talk about the system integration. Again, air pressure goes to the valve. Use the computer to control the valve. This time he used an Arduino board. I think in our project you will use Arduino as well. And he has a motor controller. This part is to control the distance between two fingers. He has a motor, I think a stepper motor, to change the distance between two fingers. And also the Arduino controls the pressure valve as well. Okay, so this is what he did. This is the experiment. He also used a camera. He put some green circular labels on top. He used a camera to study the position of the green circles. Okay. So this is image processing. He wants this to be done automatically, so he doesn't need to, do experiments manually. So basically, image processing, how you can identify the points, coordinate of the points. Okay, so this is what he has done. Study the angles between each joint. Now, he also have a grasping force. This is studying the stability. He wants to grasp an object and then try to see it. So he tried three different shapes: circular, lucky leaf, and a heart. Okay, and he applied PVDF, but this is not the graphene one. This is commercial one, already polarized. Okay, and then he applied at the the inner side of the finger. So this is what happened. He tried. Oh, there are videos. I think this is a fully released. No shells were tightened. I think the last one was all cables tightened. So you can easily see the difference. The last actuation has three portions of the fingers that were tightened by the cable. And he tried many different combinations. So he generate 8 different ways of actuating the fingers. Okay. So the extreme motion, the these are the snapshots with the maximum bending, and you can easily tell, okay, if you tighten different portions of the finger, it behaves differently. Okay, and he studied grasp different kinds of shapes. So he tried to grasp different objects. Okay, so as you can see, so he showed the best way to grasp the objects in different shapes. Okay, that's what he did. So today I have show you many different um, designs in soft robots, but most of them are for gripping design. However, in our this course, we want to apply this kind of design in a biomedical application, uh, especially for rehabilitation for rigid fingers. So we want to have a soft finger on the back of our palm, helping the patient to bend their fingers. Okay, so it's a kind of a medical device, and later on, my TA will show you what they have done so far. They use the entire summer to develop some kind of package, and they will teach you how to do how to repeat what they have done. But you don't need to copy what they have done. You can make your own design. Okay.